So today we're going to talk about light and quantum mechanics. Amplitude is the height of the wave. So if you have a higher amplitude, it takes more energy to make a taller wave. If you got a smaller amplitude, so a shorter wave, it takes less energy. Wavelength is the distance between equal parts of a wave, usually measured from crest to crest or trough to trough, but it's just any two parts of the wave that are the same. So here it's as it's going up, crossing the direction of propagation till the next one. Uh, Wavelength is given the variable lambda, lambda, and it's measured in meters. Frequency is the number of wave cycles per second, measured in seconds to the negative first, or hertz, or 1/seconds. Uh, Hertz is named after Heinrich Hertz, who did work with frequencies and stuff. So if we're going to look at this one, if this picture took 1 second for these waves, we'd have 1, 2, 3 waves in 1 second, so it'd be 3 hertz. And so that's how we would figure out that frequency. Speed of light, c, yes, it's the c from E equals mc squared, is the speed of all electromagnetic radiation that travels in a vacuum. It's about 300 million meters per second, or 2.998 times 10 to the 8th meters per second. And then we have an equation that can work with it. The speed of light is equal to the wavelength times the frequency. So if you know the wavelength and you know the frequency, you can calculate the speed of light. Obviously, since it's a constant, it should be this. So if we know the speed of light and the wavelength, we can find the frequency, or if we know the speed of light and the frequency, we can find the wavelength. Electromagnetic radiation is the radiation given off by wave particles and includes radio, radar, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays, and cosmic rays. Cosmic rays are just really high energy gamma rays that were given off by some celestial body, probably during a supernova or collision of black holes, that sort of thing. Spectrum is a range of values. In this case, the separation of EM radiation into different types. It's continuous. It never breaks. There's no stopping in between these different types of energy. We can have the entire uh, wavelength going through these if we wanted to see them differently. Atomic emission spectrum is the separation of light emitted by an element when bombarded with energy. Each element has a different spectrum, so we can identify the element with the spectrum that we see. Um, so we can send the light that we get through uh, the um, gas that's emitted from the gas through a spectrum and see, like for hydrogen, for instance, there are 4 lines. These are a little bit thicker because there's actually, I think, a couple of wavelengths here together that would make it, but a very specific amount of energy. Or if we send white light through hydrogen and detect the light that's left, we'll notice it's the exact same wavelengths that were absorbed by the hydrogen. The ground state is the lowest energy state for electrons. Only the outermost electrons can change state. So here's hydrogen. Uh, an example down here, ground state would be the lowest ring, smallest one, and the higher, an excited state would be a higher ring. It's when one or more electrons aren't in the ground state. We've got an energy equation. Energy is equal to H times nu. It's Greek letter nu. Uh, H is Planck's constant. It's another constant that we can use. Yes, we'll be given it for the test. You do not have to memorize it. 6.626 times 10 to negative 34th joule seconds. Book does a little bit of work in electron volts, and so it could be converted to electron volt seconds, sort of thing. Electron volts is just a different unit of energy. But you'll notice we have frequency here, and we had frequency here, which means if we know the wavelength, we can find the energy, or if we know the energy, we can find the wavelength, just by combining the two equations. So an example of using this equation, green light has a frequency of about 6 times 10 to the 14th hertz. What's the energy of a photon of green light? Well, energy is equal to Planck's constant times the frequency. So 6.626 times 10 to the negative 34th joules seconds times 6 times 10 to the 14th hertz. And we get about 3.98 times 10 to the negative 19th joules. I forgot to change those numbers. That is definitely not for this class. That is for Kim One's book. But anyway, a photon is a quantum of energy in the visible spectrum. Quantum of energy is just an amount of energy, a quantity of energy that is required to move an electron. Atomic emission spectra are formed by the transitions of electrons from higher energy levels to lower energy levels. So electrons get into the excited state by the absorption of a quanta. And because the Aufbau principle states that electrons have to be in the lowest energy level, they can't stay in the excited state forever. So it's unstable for those electrons to be higher up than their ground state. So they'll eventually drop down. They may drop down to the ground state right away, or they may make a transition to a lower energy level, emitting a quantum of energy for that, and then down another energy level. They don't have to do it all in one step. It's just like walking down the steps of any staircase. You might choose to take 2 steps. You might decide to have fun and jump all the way down the steps, if it's not that far, that sort of thing. Or you might take 1 step at a time. Just depends on how much energy you want to give. And you'll notice that when you're doing that jumping, it's a different amount of energy that you feel. Like if you do the full jump, your knees are going to have to bend more to absorb more of that energy than if you're walking down 1 step at a time. So when they drop back down, they emit that quantum of energy. It could be the same one, or it'll total up to be the same that it absorbed. And it correlates to a specific energy and therefore a discrete line in the atomic spectrum. That's why they're called quantums. They're quantities of energy. They have the same root for a reason. No 2 elements can have the exact same spectrum. As a result, we can determine the light that's reaching the Earth from the different distant stars and see what light is being emitted and use these atomic emission spectra to determine what elements are in there. And so if it's almost entirely hydrogen with very, very little helium, we know it's a very young star. If there's a lot more helium, it's probably middle-aged. If you got things like carbon and nitrogen in there in great enough quantities, it's probably an older star that was too small to go supernova. And so we can determine these things from just the light that gets to us. So like I said, we could have transitions in the different to different energy levels. This is for hydrogen specifically. So anytime it drops from a higher energy level down to the n equals 1, so the absolute ground state for that electron and hydrogen, it gives us ultraviolet light. It doesn't matter if it's n equal 2 to n equal 1 or n equal infinity to n equal 1. It's going to be ultraviolet light that we get, which makes sense because we know the sun is mostly hydrogen and we know that the sun emits ultraviolet light. So if we actually split it up and got the spectrum, we would notice we'd have these discrete lines. If it drops from a high energy level down to n equals 2, so it's still a little bit excited, it's 1 step up, but it's not as much energy. All that, whenever it drops to n equals 2, is what we call the Balmer series. It's in the visible spectrum. So we got one about somewhere around here, around the 4,000 angstrom mark, which is 400 nanometers. One that's like 450. They're very specific lines that we get in the visible spectrum. Different one for different energies. So violet being higher in energy, infinity energy level down to n equals 2 gives us the violet. But going from, say, n equals 3 to n equals 2 is going to give us in the red spectrum. Whenever it's dropping from a higher energy level down to n equals 3, we get the Passion series that's in the near infrared. It's called near because it's near the red. The Bracket series is from a higher level to n equals 4. It's more the far infrared. Infrared is just heat. So we know that the sun gives off ultraviolet radiation, we know it gives off light, and we know it gives off heat. So there's like physical evidence that you have seen or felt just from your own life to prove that this happens. I don't actually know what this P-Fund series is called, if it's just called the P-Fund series or what. First time I've seen it. But there's a name for each of these series. I just haven't studied any of them because it doesn't work. It doesn't matter for what I teach, generally speaking. But going down to n equals 5, we got the P-Fund. N equals 6, there's another one. And n equals 7, there's another one. So we can literally see, based upon all these different wavelengths of light that's emitted or absorbed, and match that up with known values for pure substances of hydrogen or helium or whatever, and figure out what we have. Even if we have a mixture of these gases, we can still uh, identify the most likely culprits, basically. So like if we see some hydrogen and some helium, we're going to get some lines that are, extra lines in here, but they're going to match up with the helium lines, and so we can separate the hydrogen from the helium. And even if there was another one that had something in the same exact spot as one of these, we would still, based upon the others, know which element it was, because it's not going to have all the same. So quantum mechanics. In 1905, Albert Einstein stated that the faster you go, the slower time goes. That's his theory of special relativity. In 24, Louis de Broglie suggested that particles behave both as waves, like light, and particles, like matter. The reason why we don't see it on the macroscopic scales, because the more massive the object, the smaller the wavelength. So a 50-gram golf ball that has a wavelength about 3 times 10 to the negative 34th meters. If we remember light is in times 10 to the negative 7th meters, we can see why there's a huge discrepancy. However, if we slow an electron down to the speed of the golf ball flying, it would have a wavelength of 2 times 10 to the negative 5th meters. So now we would be in the microwave range. Classical mechanics is great for explaining and simplifying the macroscopic world, but breaks down in the microscopic nanoscopic world. So Newton created calculus to describe physics, and basically through, if you've taken calculus, which I don't know if you've taken any or not, but basically one of the things that we see is we go from estimating a graph with a curve or whatever by making these rectangles and adding up their uh, uh, areas. And by getting that area underneath the curve, the smaller and smaller these get for these rectangles, the closer to this we would get. And so he basically simplified quantum without knowing that quantum existed to the classical world. Quantum mechanics is great for explaining all matter, both macroscopic and microscopic, but because the equations can be very complicated, if we can use classical mechanics, so we're dealing with big things, we're going to use classical mechanics. If we're using something that's very small and very fast, we're going to use quantum mechanics or some derivative thereof. And you notice, for classical mechanics, we got this ramp that slowly increases energy. This would be like your continuous spectrum. And on quantum mechanics, we've got very specific energies for these steps, just like hydrogen can only have specific energies in its atomic spectra. Heisenberg's uncertainty principle states that you can't know both the velocity and position of an object, because in order to know one, you have to change the other. So in order to find an electron, you have to hit it with something like a photon. Since those are close enough in mass, you end up changing the path of the electron. So if you located the electron at that moment, you know everything about the position at that moment, but you know nothing about the momentum afterwards or the velocity. So we can't figure out the path and things like that. It's like playing dodgeball in the dark, although without glow in the dark stuff to help you identify. If you hit somebody with the ball, you can hear it, you know where they're at that moment, but you can rest assured that they're probably not going to stand still to be hit by another ball. So they've moved. So you knew something about the position at that point in time, but you didn't know about their motion afterwards or what happened to